Okie dokie everyone, here is the walkthrough for that last part of the higher tier paper. So this is everything that only the higher tier students see. So we're starting on question 3 now. A hybrid car has an electric motor and a petrol engine. Petrol is a non-renewable energy resource. What is meant by non-renewable energy? There's lots of possible wrong answers here. Ones that we can't take is reuse. It is about being something that can't be replenished. As in, there's not a ready supply once that's used up. In the case of fossil fuels, it takes millions of years to form that new fossil fuel, whether it's oil or gas. Winds can be replenished. Okie dokie. The next question here is the electric motor in the car is powered by a battery. To charge the battery, the car is plugged into the main supply at 230 volts. The power used to charge the battery is 6.9 kilowatts. Right, there goes your klaxon. My klaxon's just gone off because I saw kilowatts rather than watts. So I know straight away I'm going to need to do something to that. And that means I'm going to have to do something with the number 1000 for kilo. Put in kilowatts into watts, I would have a lot of them, so I'm going to times by 1000. Okay, I've got to work out the current used. I've got current, power, and main supply. I didn't really say what that is, but I do have the units there in V volts. So that must be the potential difference then. So I've got current, power, and potential difference. That equation is P equals I times V. Substituting in, we've got 6,900 from that, which times 1,000, times by the current I, which I'm trying to find out, equals I times 230 volts. We now need to rearrange this, so I want to get rid of the times 230 and divide by 230. That cancels out that. And your answer in this case works out to be 30 amps. Okay. Mains electricity is an AC supply. Explain the difference between direct and alternating potential difference. Okay, this was really poorly answered. In the case of a direct current, these are things like cells, solar cells, where they just push the current round from positive to negative in one direction. And it only goes in that direction there. It's exactly the same as a bicycle wheel. The energy is transferred from the pedals over here to the wheel, and it just goes round in one direction, transferring energy through instantaneously to the back wheel. Alternating current is where you plug into the mains, and it has this little wave symbol. Because it alternates, it changes just like a wave does. And so what happens here is, if I go for blue this time, what happens here is the current will be heading in that direction, but then it will switch and it will head in that direction. And it alternates backwards and forwards. So the current will alternate backwards and forwards like that. Now in that sense, some people who might not quite get how current works and thinks that it has to deliver something and take time to might be a bit confused at this point. But if we go back to our bike analogy, and let's just say we've got a fixed wheel bike here. If you pedal the bike, the pedal forwards and backwards like that, so you push it forwards then come back up again. If that's fixed wheel, that wheel is going to go back round and then switch direction. It's still going to move. It won't work as a bicycle. You'll be going backwards and forwards, but in the principle is you are still transferring energy from here to here. So the potential difference just goes backwards. The potential difference switches between positive and negative, pulling the current in one direction and then the other. So explain the difference between direct current, the direct potential difference pushes the current in one direction. Alternating current, it switches direction. Okay, the cable used to connect the car has a low resistance. Explain why it's better to use a cable with a low resistance than to use a cable with a high resistance. Okay, I think the most obvious point here is if you've got a high resistance, you're going to have a low current. I think that's fairly straightforward. There's 2 marks there. We know if you connect it to the main supply, it's going to be at 230 volts. So you could go back to that P equals I times V equation. And you could be thinking, if I've got a low current, and the potential difference is just constant at 230, having a smaller current means I'm going to have smaller power transfer. And if we then consider what power actually is, or power, as hopefully you know, is the rate at which you transfer energy. So if you're trying to fill your car up with a certain amount of energy and you've got a lower power, that lower power means it's going to take longer to transfer the same amount of energy. So in terms of marks, 1 mark for talking about low current, and a second mark for talking about it would take longer, or vice versa. A high current means it could charge quicker. Next one. So we now have this circuit here, and we've got a question about the resistors. Now we've got the lamp here with a resistance of 10 ohms. We've got that resistor of 10 ohms and 10 ohms. And what's the total resistance of the circuit? Well, the point here is that we would have, when you've got resistors in parallel, because the current now has 2 ways that it can go, you've actually got a lower resistance than what you've got here. So if you've got 10 ohms there and 10 ohms there, that therefore would give you a total resistance of less than 10 ohms for that little parallel loop. It's the difference between this. If you consider going to the canteen and you've got 2 doors to go through, like parallel doors, doors in series, and you've got to go through there and through that door. And if I've got to get the whole of year 11 through those doors, that has a certain resistance. Let's call the resistance, I don't know, 10 ohms and 10 ohms again. Now in series, you would say you've got a total resistance of 20 ohms for that corridor. If you, however, put the doors side by side to the canteen, and you now have your year 11s going this way, and some can go that way and some can go that way, your total resistance is going to be less than 10 ohms. So, which means if I've got 10 ohms here and less than 10 ohms here, my total resistance is less than 20 ohms. Okay, so a little bit of important bits there, but the most important is when in parallel, the resistance is less than the sum. And that would account for question 2. The current has both ways to go, so there's lower resistance. Okay, on to the next one. Circuit symbol for a thermistor. Thermistor, break it up. Therm means cold. Istor is for a resistor, so you draw a resistor, and then you draw an ice hockey stick, because if therm's to do with temperature, ice hockey stick, you'd be feeling cold. That's my silly little link. Right, student, increase the temperature of the thermistor. Explain how the current in the thermistor changed. This was testing your understanding and your knowledge, really, just recall, of this graph here. And this graph is of the resistance of a thermistor. They could ask the exact same question looking at a light-dependent resistor too. And rather than a thermistor where we're looking at temperature, they might actually do this as light intensity. Either way, it has the same graph, and that is this. So if we increase the temperature, the resistance drops. The student increase the temperature of the thermistor, the resistance drops. We've got to explain, so we've got to give some reasons for it. The resistance drops, therefore the current must increase. So that is what happens, and that is our explanation for why. Okay, this question here is 4 marks. There's quite a lot to go through in this. So I'm going to put some made up numbers to this. If you remember from the previous question, this was a 10 ohm resistor, and this was a 10 ohm bulb. And let's just say for the purposes of ease, we just say it's a 2 amp current flowing through from positive to negative. So the current is going to flow through the bulb and then flow through here whilst the switch is open. If that's the case, then for that resistor here, V equals I times R from our Ohm's law equation, 2 amps times resistance, which is 10, gives us 20 volts. So I'd actually have 20 volts there. Okay, let's just say we have 40 ohms going in. 40 volts going in. That means I must have 20 volts there, because in a series circuit the potential difference is shared. Those numbers might help make this a little bit easier when we talk this through. So explain how the potential difference across the resistor and the lamp will change when the switch is closed. Okay, so in this case, if we close the switch, what we end up doing is we end up making a circuit around there. So now the current, it does have the choice of going through this resistor or the short circuit. However, there's very, very little resistance. We'd say in technically it's not. In reality, there is a little bit of resistance, but we're going to say in theory there's no resistance there. So the current is all going to flow through here pretty much. What that means is if this current here flows, if there's absolutely no current flowing through here, then if we go back to our equation, then the current here drops to 0. 0 times 10 gives us 0 volts. In other words, I've got no current flowing through, so it cannot transfer any energy to the resistor. And if you remember right, potential difference is the amount of energy each coulomb of charge is able to transfer. We've got no current, so we can't transfer any energy, so the potential difference is down to 0. So if we say potential difference goes to 0 volts, it's because the short circuit and the current, sorry, I'm writing current, flows through this short circuit. Right, considering those numbers then, so if all of a sudden we now have, and we go and we've got no potential difference across that resistor, well, I'm still putting 40 volts in. Well, that 40 volts has got to go somewhere. So that means that 40 volts is all going to go to the bulb, so the bulb will get brighter. So in this case, the potential difference increases. Now you could talk about how the potential difference must all go to that. You could just say more generally though, because we've got less resistance, we've got a bigger current as well. So we're going to have more energy transferred to that bulb. Or because we've got a low resistance in the whole circuit. So potential difference increases because we've got greater current due to a lower resistance in the whole circuit. Okay, the heating element of this kettle question, I won't go through all of it. This stumped quite a few of you. In fact, most of the people that have, pretty much everyone. Explain why the temperature of the heating element increases. Well, it's an electrical heating element, and so essentially current is pretty much just flowing through the live wire up here, round through the element and back out through the neutral wire. So why does it get hot? Well, this is down to the exact same physics behind why a filament light bulb glows hot and how its resistance increases. So if you can remember that, and the idea that if you plot a potential difference against current graph, for a fixed resistor it should follow Ohm's law like that, but for a filament bulb it does that and curves around the other way. The resistance gets higher. Now when we went and did this, the explanation for this is the exact same explanation for what's going on in the heating element. As the current passes through, it's passing through the particles in the metal. We call these the metal ions. So it's passing through the particles, and at high potential differences we have a higher resistance. And what's happening is all these electrons, I've got much more flowing through now, they all collide with the metal ions or the particles. They vibrate more, which means a higher temperature. In this experiment, one variable that the student could control, the most obvious one is the one we want here, is the starting temperature. Okay, why does figure 5 not go through the origin? If you have a look at the question here, this shows us how the mass of water in the kettle affected the time taken for the kettle to switch off. Time taken up this side, mass over this side. So when I've got no water, it does take a second. It doesn't go off instantly. It takes 5-10 seconds to go off. Why is that? Well, when you start it, you've still actually got to heat up the heating element. So the heating element needs to warm up. Okay, this was a really tricky one here. Suggest why the results give a non-linear pattern. This keyword here, suggest why, the command word, means we've got to give reasons for it. Now, it is just a one mark question. But I think what we can see from the graph is there's a lot of explanation here that could kind of show you how to really analyse these graphs. Okay, if we have a quick look at the graph here, it seems to curve, and that's what we're getting at here. Now, you can't just say it's non-linear because it curves. That's kind of obvious. We're trying to go for the reasons why it happens. So we start off at 10 here. Let's just have a look at that first. Let's analyse what the curve means. What it means is in that first 200, for the first jump of 0 to 200 grams of water, by increasing by that much, we get an added increase of 15 plus another 15, which is 30 seconds. It takes 30 seconds extra to jump from 0 to 200. If we go from this side here, another jump of 200 here. This time we've gone up by 1 square, 2 square, 3 square, 4 square. So we've gone up by just 20 seconds in this case. So the jump, the increase in extra time taken by adding another 200 grams, it's not linear. We're getting, it seems to be a bit quicker for that extra 200 seconds. Well, why must that be? Well, if it's a bit quicker, that means we're clearly not losing as much energy. All that energy is going in to raising it to the right temperature, and therefore allowing it to switch off a little quicker than you think it would have done had it been a straight line pattern. So for that reason, you could then just boil it down to talk about how if less energy is being lost, you could say it's more efficient at greater masses, or when there's a greater mass of water in the kettle. Okay, this is a classic 6-mark question. This is about your knowledge of equations. You need to have the 23 equations app, and you need to be recalling them, because if you can get this 6 marks, it's a bit of an open goal essentially if you know your equations, and with a bit of practice, obviously. So we've got here the power of the kettle was 2.6 kilowatts. Klaxon's just gone off. That's kilowatts, so it should be in thousands. So that's 2,600 watts. I'm going to change that straight away. Kettle took 120 seconds. I'm just going to write there. That appears to be talking about time. To heat 0.8 kilograms of water. That seems to be talking about mass. And I've got a temperature change here from 18 to 100. Now, if I think right, This is going to be specific heat capacity, and yes it is. I've got to calculate specific heat capacity. Now I know from the equation on the equation sheet, which you are given, that change in temperature is important. So the change here is 82 degrees. Okay, so let's have a think. If you're going to work out specific heat capacity, then kind of obviously the equation we're going to need is mass times specific heat capacity times change in temperature. There's a reason why I've written this lower down, and that's because I know in these 6-mark questions they're going to need another equation beforehand that helps feed into one of these points, one of these variables that I don't yet have. So let's just have a quick look and think. It must be that equation because I've got to find specific heat capacity. Let's just see what I've got so far. I'll use a couple of colours to help us highlight this. So change in temperature we have there. Specific heat capacity we're trying to find out. So that is obviously just our missing value, our question mark. Mass we're given here. And so what I'm now looking for is energy. And I don't appear to have energy. But what I do have is I've got power. And I also have time. So the second equation that you needed to refer to has to find energy. But I'm also given power and I'm given time. So what is that equation? Well, it is the P equals E over T equation. In some of the revision guides, it just rearranges it for you straight away, or communicates it as E equals P times T, which actually is quite useful for this. Just to be uber pedantic, I'm going to leave it as this equation here, and we're going to go 2,600 in there equals the E I'm trying to find out divided by 120. If we then rearrange this, I need to get rid of divide 120, so I'm going to take that up there and times by 120. That cancels that out. E therefore equals 312,000 joules, and that is what goes into here. So now we've actually got relatively simple calculation, which you guys should be eating up really. So I've got 31200, sorry, nearly missed one, equals the mass, which was 0.8, times C, which I'm trying to find out, times the change in temperature, which is 82. Now what we're going to do is simplify it, which equals 65.6 times C. I'm going to get rid of the thing that's stuck next to C, times 65.6. I'm going to divide by 65.6, cancelling that out. And that gives us C as 4,800 joules per kilogram degrees Celsius. And that goes to two significant figures rather than what comes out of your calculator, which is 4756. So the 6th mark there was for this two significant figures, so try not to forget that. Always go back and recheck your responses. Okie dokie, right, this is, we're on to radioactivity now, and we're on to some tricky questions here. Lanthanum-140 emits gamma radiation apparently. What happens to the mass number and the charge of the nucleus when gamma radiation is emitted? Well, this is back to your recall. Alpha has a mass of 4 and 2 because it is 2 protons for that bit. 2 neutrons, meaning we've got 4 in total. Beta is a fast moving electron, so it is no mass. Oh, sorry, don't know. Gamma sign, silly me. No mass, but -1 charge. Gamma, however, is an electromagnetic wave. So gamma has no mass and no charge, which means if you're not taking any mass out and you're not taking any charge out, the mass stays the same and the charge stays the same, so that must be our right one. Why is it difficult to detect gamma radiation? Well, it doesn't interact very much. It penetrates. It's highly penetrative. So for that reason, it's not going to be stopped. So it's not going to be stopped by your gamma tube or your Geiger-Müller tube. Okay, activity is the rate at which a radioactive source decays. This definition here given to you is going to be useful later on. It's the rate at which radioactive source decays. A teacher measured the count rate from a sample of lanthanum using a Geiger-Müller tube. Explain why the count rate was less than the activity of the sample. Well, if the activity is the rate at which it decays, and our count rate is what we measure, well, it's kind of just a bit of a kind of obvious one, really. Probably not that obvious because we don't get to do this experiment that often. However, if you've got a sample here, let's just say here is my cup source that I got out when we did radioactivity. This is giving off gamma radiation all around. Well, that might be the activity, the rate at which it decays. However, my count rate, my counts per minute, is only from what comes into the tube. So of course that's going to be less because you've got all of these around here that are not going to be going into the tube. You've also got some who are just going to pass straight through because gamma is so penetrative. Okay, explain. We've got to give reason why for 2 marks. Explain why the teacher stood as far away from the apparatus as possible. Well, there's kind of a little bit obvious for this, really, and that is just to reduce the radiation that is absorbed. Again, if you remember, this is irradiation, not contamination. Contamination is when you get a bit of that radioactive material actually on you. Right, so we've said initially that reduced radiation absorbed, so we've got 1 point. Second point, we've got to explain why they've done that, and that's because it causes cancer or genetic mutations. Technically, you would say it increases the risk rather than causes straight cancer. Okie dokie. A numeracy one here. Right, inversely proportional. We all know that directly proportional is that. We've done that with V equals I times R. We've done it with lots of things. Inversely proportional is this. And basically, there's a simple way of finding out whether something's inversely proportional. If you take 2 values, so 2 corresponding values, let's say the red one and the blue one, if this data is inversely proportional, then multiplying those 2 together should get you a number. Actually, let's not call it question mark, let's call it X. Multiplying those 2 together should also get you X, and multiplying those 2 together should get you X. That is a very specific relationship. It's not just a simple curve. It's not the same for any curve, like a curve like that or a curve like that. It is a very, very specific relationship. We apply this to the data that we've got here. Let's take 2 values, and let's take that one, and then let's take that one and that one. Let's multiply them together. And in this case, you will get 55, and in this case, you will get 36. So therefore, they are not producing the same number as what we should have in an inversely proportional relationship. So it's not. So to get the marks, you've got to say that, first of all, produce 2 calculations by multiplying the 2 together. And then final thing saying, stating that they are not the same number, therefore it can't be inversely proportional. Right, we're on to difficult question now. This is really hard. We're going to talk about half-life of the isotope, and it shows how the number of atoms, this cerium, changes over time. So we've got to have a look first of all about anything interesting about this. Whenever you've got a graph of decay, I think it's pretty much common sense to have a look at the half-life straight away. So let's go down to from 5 to 2.5. And how long did that take? Oh, and interestingly, that took 50 seconds. So it's always worth working out the half-life of this, and the half-life appears to be 50 seconds. Back to the graph now. What is the rate of decay over here? Well, let's get rid of this bit here. I think it said when it was 20 seconds old. So the rate of decay. If you know clearly from maths what a rate is how much something changes x per second, or a change in y over a particular period of time. So examples of rates of change in chemistry is the rate of reaction. For example, the amount of mass that gets reacted per second. In physics as well, you've got acceleration is the rate of change of speed, how your speed changes from your final speed to your starting speed, how much that changes per second, and you've got various other ones. What that would look like in a graph is essentially these things are gradients on graphs. For example, the acceleration one, if I have speed against time, the gradient would tell us what's the acceleration is. So from that same notion, the gradient in this, because this is a graph of atoms of cerium over time, and we need to know the decay, the rate of decay, we're going to need to work out the gradient of the graph. The tricky thing from this, though, is it's a curve. So what we need to do to work out the rate of change is we need to have a tangent, and I'm going to attempt a tangent there, which is a straight line which glances the line at 20 seconds and extending it down. And what I'm now going to do is, because I've gone to the axes, I'm going to use the full axes to work out the gradient. And in this case, I'll go from 0 to 4.7. So I've got a change of 4.7 in, well, that's nice and easy, 90 seconds. So 4.7 divided by 90 would give me my gradient here, and that would be your answer. So we would have accepted anything between sort of 4.7 to 5.9, so obviously a tangent is going to be a bit wonky, so there was a bit of leniency with this. In the case of my results, it was 0.052. I'll have a look at the number here, times 10 to the power of 23, so we've got to include that, times 10 to the 23. And if I put that actually in standard form, move that back 2 places, it's 5.2 times 10 to the power of 21. And activity is in becquerels, but I think that was radioactive decay graph. And the first thing is determine the ratio of number of cerium atoms in the sample when it was 100 seconds old compared with when the sample was 350 seconds old. This is 4 marks. So, well, let's head back to this. Got a half-life of 50 seconds, and that rings a little bell with me because if I'm going from 100 to 350, I can do that in 50-second jumps. So if you remember, the half-life means every 50 seconds it halves. So if now we consider these 50-second jumps, we're going to say we're starting here, and in 50 seconds it halves. So we now have 1/2 of what we had before. We therefore must have started with 1 whole. Let's just say we've got 1 whole. Then we've got a quarter or a half. It halves again, so we're down to a quarter. It halves again, so we're down to 1/8. It halves again from 250 to 300, and we're down to 1/16 or a half of 1/8. And then from 300 to 350, we're halving again to 1/32. So we can also say, therefore, that our ratio is 1/32 from here compared to what we started with. Okay, next question then. This is a really tricky one. Determine the activity of the sample when it was 20 seconds old. Now, if you remember from the previous couple of questions ago, when I said we're going to need this later, it said the activity is the rate of decay. of the sample. So it actually kind of told you a definition for activity. Rate of decay was seconds old, didn't it? Yes, you in the question there, yes. Okay, tricky question, but there's loads of stuff to get your teeth into there.